Okay, so in this video, we're going to be deriving the position equations for a 4-bar linkage. And to start, what we really want to find out with these equations is where are the links at any given moment and how fast are they going? And the reason that information is useful is because you can use it to derive output forces, output torques, mechanical advantages, etc. So here we have a geometric diagram, and we've represented each link here, A, B, C, and D, D being the ground link, with vectors. So A is represented by R2, B is represented by R3, C is represented by R4, and D is represented by R1. Now, let's kind of go through the variables in this geometric diagram. Theta 2 is the angle of the input link, so the angle of link A. Theta 3 is the angle of the coupler link, or link B, and we've chosen the local axes to be such that x3 goes this way, y3 goes this way. Theta 4 is the angle of the output link, so we've chosen the local coordinate axes here to be similar as how we have with the coupler link. So theta 4 is this angle right here. The magnitude of R1 is D, the magnitude of R2 is A, the magnitude of R3 is B, and the magnitude of R4 is C. And you can kind of see that here. R2 is represented with our input link, R3 is represented with our coupler link, R4 is represented with our output link, and R1 is represented with our ground link. So our xi, yi, these are the local axes such that they are parallel to our global axes, big X and big Y. These local axes just help us maintain our vector directions as the links move in space, right? So what we need to do with our thetas here, so theta 2, theta 3, theta 4, is determine what our sign convention is. So what we're going to use is a very common sign convention in vector math, and that is theta is positive counterclockwise with respect to east. So if you kind of draw a projection out to the right, theta is positive counterclockwise from that projection. So theta 4 is positive here, theta 3 is positive here, theta 2 is positive here. Now if you go in the opposite direction, clockwise from that projection east, so to speak, you have a negative value. So theta 4 is negative here, theta 3 is negative here, and theta 2 is negative here. So one fundamental assumption we're going to have here is that we have a closed linkage, meaning that our link diagram, as we have drawn here, can be represented essentially by a closed polygon of some kind. Now, open links tend to be much more complicated and harder to analyze, so fortunately, we can just assume a closed linkage here, something like you might see a crank rocker or a double rocker, something to that effect. Those are all closed linkages, typically. So what we're essentially saying here is each link in this closed linkage can be represented by a collinear vector of arbitrary direction. So the head or tail of the vector that we use to represent the link can be placed at either end of the link. Just remember to take the angle of the vector from the root, because we always take the angle of the vector from the root. So here, we've drawn R2 in this direction, R3 in this direction, R4 in this direction, and R1 in this direction. You can choose any direction you like. R2 could be drawn like this, R3 could be drawn like this, etc. You just have to remember to take the angle at the root of the vector. This is just arbitrarily the directions that we've chose, and therefore the appropriate angles corresponding to those arbitrary directions. So the next thing we're going to look at is the vector loop equation, and essentially what that is a particular sum of vectors around the closed loop equals 0. So the form of the sum is a function of the established geometric diagram, specifically the directions of the vectors that you've chosen. So if we look at our geometric diagram here and our arbitrary directions for the vectors that we chose, we could see that, well, if we take R2 and add it to R3, we have this diagram right here. This is the sum of R2 plus R3. So we have this sum of R2 plus R3. Now, if we take R2 plus R3, as we have right here, and we subtract R4 from it, which is this vector right here, it's essentially saying, well, take R2 plus R3 and add it to negative R4. So what we can do is just kind of draw R4 in the opposite direction, which we have here, and then perform that summation. So this is the sum R2 plus R3 minus R4. Now, R2 plus R3 minus R4 added to negative R1 is such that we have a vector that goes horizontally like this, and a vector that goes horizontally in the opposite direction like this. If you add this vector to this vector, the sum is 0. So essentially what we've done here is we found an equation that closes the position of the linkage. So R2 plus R3 minus R4 minus R1 is equal to 0. So this sum just comes from this logic right here. So essentially, again, you're just saying, well, r2 plus r3 gives me this vector right here. If I take r2 plus r3 and I subtract r4 from it, I get this vector right here. Then if I have r2 plus r3 minus r4 and I subtract r1 from that, I get 0. Now again, depending on the directions you've chosen for your linkage, your vector loop equation may look a little bit different. The signs may look a little bit different, but this is the logic. Essentially, there's some summation that you can formulate with your closed linkage such that your vectors equal 0. And you need this equation to close the system mathematically, and we'll get into that next. So the next step, before we kind of dive into things and use the vector loop equation to derive the position equations, what we need to do is determine an equation for each vector in the vector loop, right? So how are we going to represent the vectors? So R2, R3, R4, R1, how are we going to represent those vectors component-wise? So often in mechanism analysis, we will represent our vectors with polar forms. So we use an imaginary component and a real component in 2D to represent our vectors. And it's kind of weird. We're going to go into that, how that works now, but it does make a lot of sense mathematically, and we'll also see why it makes sense mathematically, particularly when we go to velocity analysis, which will be another video. But to begin, let's say we have some arbitrary vector RA. What we could say is, we could say that RA is equal to R, the magnitude of RA, times e to the j theta power. And Euler's identity says e to the j theta power, which you see right here, is equal to cosine of theta plus j sine theta, or e to the negative j theta power is equal to cosine theta minus j sine theta. Now, if we were to represent our vector with this form right here, essentially what that would say is, okay, so we have r times cosine theta plus jr times sine theta, which just comes from Euler's identity plugged in here, times the magnitude of the vector r distributed to both terms. So what we're going to posit then is that this is equal to rx plus ry. And again, the magnitude of RA is equal to R, as represented here. So this form of the vector RA is called our polar form of the vector. This right-hand side, so again, the left-hand side is our polar form. The right-hand side is our kind of more typical Cartesian form, where you have an x component and a y component. So again, our Euler's identity just converts from our polar form to our Cartesian form. This is kind of our polar form. This is our Cartesian form. Now again, you may be saying, okay, I kind of see the outlines, the architecture of a Cartesian form in this right-hand side, but I don't see my unit vectors, right? I don't see my I hat, I don't see my j hat or k hat or whatever. And the reason is because we don't have them in this version of our Cartesian form. So essentially what we have is, in the 2D plane, any term without a j, where j is not j hat, j is the imaginary unit, so what you might more typically represent as I, the square root of -1, but we call j. Any unit without a j, or any term without a j, is an x component. Any term with a j is a y component, right? So again, j is not j hat. J is really what we would call I in mathematics, or the square root of -1. It's the imaginary unit. We're just calling it j here. It's just a standard notation to call it j in mechanism analysis. So any term with a j is a y component. Any term without a j is an x component. And we kind of have that written again here. Terms with a j multiplier are y components. Terms without a j multiplier are x components. So again, this j or no j approach, this polar approach, is different from using standard unit vectors like I hat, j hat, k hat to represent components in the plane. But it's just as valid, right? It's just as valid, and we will see that. So you might be asking, why are we going through all this effort? Why don't we just use standard Cartesian forms? And again, like I mentioned before, the mathematics ends up being a lot easier if you represent vectors in this kind of polar format than the standard Cartesian format, and we will see that in subsequent videos. So the next question is, does this vector equation hold for any vector in the plane, given how we define theta? Again, theta, the convention for theta being positive counterclockwise relative to east. So does this vector equation hold? Prove to me that this vector equation holds, like our Cartesian vector would, right? So let's go through that proof now. So what we have here is a vector in each quadrant of the Cartesian plane. And we show that the polar formulation of the vector, no matter which quadrant it's in the Cartesian plane, is an accurate representation of that vector. So whether it's in the first quadrant, the second quadrant, the third quadrant, or the fourth quadrant, the polar form accurately represents the vector. And So I won't go through all 4 quadrants here, but let's go through the first example. Let's maybe look at B here. So here we have a vector in the second quadrant, right? So our theta is greater than 90 degrees. It is positive because it's counterclockwise from east, which is this projection right here. So this theta is positive, but it is greater than 90 degrees. So first things first, we have now established that our theta is greater than 90 degrees, but because the vector is in the second quadrant, it's also less than or equal to 180 degrees. So theta is between 90 and 180 degrees. So what does that mean? If theta is between 90 and 180 degrees, sine of theta is greater than or equal to 0, and cosine of theta is less than 0, right? Think about your unit circle. These two things are true in the second quadrant. So if we say that Rx is the magnitude of our x component vector, and Ry is our magnitude of our y component vector, Re is our real axis, or the x-axis, and Im is the imaginary axis, or the y-axis, then what we end up having is, what is our Rx? Well, our Rx is this vector right here. And this vector right here is equal to r times cosine of 180 degrees minus theta. So what does that equal? Well, through trig identities, we see that r cosine of 180 degrees minus theta is equal to negative r cosine of theta, which we know from this fact right here, negative r cosine theta is greater than 0. So our Rx, the magnitude of our x vector, is greater than 0, as it should be, because it's a magnitude. Ry, now let's look at Ry. Ry is this vector, or really this vector right here, right? Ry is equal to r times sine of 180 degrees minus theta, which is equal to, through trig identities, r sine of theta. Through this factoid right here again, we see that r sine of theta is greater than or equal to 0. So Ry, a magnitude, is greater than or equal to 0, as it should be. So essentially what we have right now is our polar form is currently telling us, hey, your magnitudes are positive, right? Which is correct, they're magnitudes, they have to be positive. If our polar form was saying, hey, your magnitude is negative, something's wrong there, right? So we would know that that's some kind of indicator that maybe the representation is not valid. Here, our polar form is saying your magnitudes are positive, as they should be. So that's a good sign. So we see that Rx and Ry are positive when represented in the polar form. Now you might be wondering, where's this 180 degrees minus theta coming from? If you look at this angle right here, it's 180 degrees. Minus theta gives us this angle right here. So cosine of 180 degrees minus theta gives us the cosine of this angle. That's Rx. And then the same, sine of this angle, right, gives us Ry. So that's simply 180 degrees minus theta is just this angle right here. And we're really dealing with this triangle with this leg being Ry, this leg being Rx. So now let's look at our component vectors. Now, again, these are component vectors, but they are still vectors. So they have a magnitude and a direction. And we're going to use the polar logic to represent these component vectors. So Rx. Rx is this magnitude right here, but it is in the negative direction. And because it's an x component, we do not associate a j with it. We just say, okay, Rx is equal to negative Rx. Because there's no j component, we know that it's an x component, right? So Rx is in the negative direction, it's an x vector, so we just say negative Rx is equal to our Rx vector. Now, we know what Rx is. It is negative r cosine of theta. So negative r cosine theta is positive r cosine theta. Now again, because we don't have a j component, we don't have a j term, we know that this is an x component. That's simply the arbitrary thing that we've decided to represent these polar vectors with. J equals y component, no j equals x component. So there's no j, so this is an x component. For Ry, we see, this was Rx, now this is Ry. It's in the positive direction. So we have positive j Ry. Why is this j here? Because it's a y component. So all y components have a j term. So we just tack on a j here. So positive because it's in the positive direction. J because it's a y component. Ry because that's the magnitude of the y component of the vector. So what is Ry? Well, it's r sine theta. So what does that equal? Positive j, that's a j, r sine theta, right? So that's the y component of the vector. The overall vector Ra, which is this vector right here, is just equal to the components added together. So Rx plus Ry, well, we know what Rx is positive r cosine theta, right? And plus, because we're adding the components together, the Ry component, positive j r sine theta, positive j r sine theta. So this is Ra represented in our polar form, right? Kind of the Cartesian version of our polar form. So what this ends up equaling is, well, what is r cosine theta plus j r sine theta equal to? Well, factor out the r, and then you have cosine theta plus j sine theta. Well, you have cosine theta plus j sine theta. That's just Euler's identity. That's this term right here. So that's equal to e to the j theta power. So if we factor that r out, we get r times e to the j theta power. R times e to the j theta power. So this polar form accurately represents this vector right here in the second quadrant, right? So again, this is kind of the Cartesian version of our polar representation, and this is the polar version of our polar representation. But regardless, the polar form is representing this vector correctly in the second quadrant. It also represents the vector properly in the first quadrant, the third quadrant, and the fourth quadrant. And these proofs are all similar. And essentially, what this is proving, again, is the polar vector form r to the ej theta power correctly represents any vector in the Cartesian plane with the positive counterclockwise relative to east vector direction convention. Okay, so again, now that we've kind of established that, here's our formalism or generalism here. And again, we have our real axis, which represents the x component, and our imaginary axis, which represents the y component. We have some arbitrary theta, which is just showing something in the fourth quadrant here, some vector in the fourth quadrant. And this vector RA is equal to r times e to the j theta power, which is equal to r cosine theta, which is our x component, plus jr sine theta, which is our y component. Again, with the magnitude of r equaling r. Okay, so now that we are comfortable with that, we kind of understand where it's coming from, we feel that it does accurately represent the vector regardless of where it is in the plane, because again, a linkage could be anywhere in this Cartesian plane. You could have, let's say we're looking at our input link, maybe it is here, maybe it's spun over here, maybe it's spun over here, maybe it's spun over here. We need to be able to represent that link, you know, whether it's the input, coupler, output, ground, whatever, anywhere it is in the Cartesian plane. So the next step is substitute the equation for each vector, which is this equation right here, into the vector loop equation. Well, again, our vector loop equation is r2 plus r3 minus r4 minus r1 is equal to 0. And we have the polar form for each of those vectors right here. So what does that equal? Well, it's just r2 e to the j theta 2 plus r3 times e to the j theta 3 minus r4 times e to the j theta 4 minus r1 times e to the j theta 1 is equal to, well, what is R2? It's A. What is R3? It's B. What is R4? It's C. What is R1? It's D, right? So we substitute that in, and that whole sum is equal to 0. That is our first equation, essentially. That's equation A, if we call, you know, really our first equation is this vector loop, but let's just say equation A is this simplified form right here. Now, through Euler's identity, which again, we have right here, e to the j theta is equal to cosine theta plus j sine theta. So through our Euler's identity, we're going to take each of these terms and plug in kind of the Cartesian version of the polar form, right? So here's our a cosine theta 2 plus ja sine theta 2, which is from this, plus b cosine theta 3 plus jb sine theta 3, which is from this, and then we kind of go down through the other links as well. So we're just taking our e to the j thetas and using Euler's identity to replace those e to the j thetas with the Cartesian version of the polar form. So again, our cosine theta plus sine theta summations, where our j's again represent the y components and our no j's represent the x components. On the next slide, what we could say is, well, if we have our sum again, but we remember that theta 1 is equal to 0, and again, why is theta 1 equal to 0? Well, what is theta 1? Theta 1 is the angle of the ground link. The ground link is defined as kind of the frame of the mechanism, right? It's not really moving. Everything moves relative to it. And we kind of define here, as you can kind of see, its angle is 0. So theta 1 is kind of almost defined as 0. Again, it's the angle of this link right here. If you kind of think that what's the local coordinate system of D or R1, well, you can kind of assume that it's capital X and capital Y. R1's angle relative to capital X is 0. And with that, we can go back to where we were, and that is right here. So because theta 1 is equal to 0, we can simplify this equation right here with this equation right here. Now again, we have these two terms, we have these two terms, we have these two terms. Now, cosine of theta 1, if theta 1 is 0, is just 1. So you just get the minus d here. Sine of theta 1, if theta 1 is 0, So this term just disappears. So that's where the minus d comes from. This term disappears, and this term just goes to d. So with that, we're going to group our x and y terms. Again, and I know I've said it quite a bit, the x terms are the terms without the j multiplier, and the y terms are the terms with the j multiplier. So group our x and y terms. X terms have no j, so we group those terms. Plus, we group our terms in y, the terms with j. Here we go. And then we factor out our j, right? So we have this summation, no j, plus this summation with a j. X components, y components. And again, This is from the vector loop equation, so this sum is still equal to 0. Now, two equations result from this, right? So essentially what this is showing is this is one big vector component in x, and this is one big vector component in y. And essentially it's saying that these two vector components, when added together, are equal to 0. The only way this can be true is if each vector is equal to 0, or if each magnitude of each component of the vector is equal to 0. So this term has to equal 0, as you see here, and this term has to equal 0, as you can see here. And those are equations B and equation C. So now we're starting to get a simpler formation of our vector loop equation, of our position equation for our 4-bar linkage. Now, one important assumption here, theta 2, the angle of your input link, is assumed to be known. So for example, if your input link is attached to a servo or a stepper or a brushless DC motor or something like that, there's some kind of controller or some kind of encoder, some kind of Hall effect sensor, some kind of feedback that you have such that you know the angle of that input link, right? So we're assuming that theta 2 is known because it is there's some kind of sensor or some kind of software that's giving you feedback that's telling you where theta 2 is, right? So we're assuming theta 2 is known. And the geometry, A, B, C, and D, the lengths of the links, are also known. So at this point, what we have are two equations and two unknowns. You'll say, okay, so what are the unknowns? Well, theta 2 is known. Theta 2 is known. A is known. A is known. B is known. B is known. We don't know theta 3. C is known. C is known. Theta 4 is not known. D is known. So the two unknowns are theta 3 and theta 4, the angle of the coupler and the angle of the output link. Everything else is assumed to be known. Okay, so moving on. The solution of these two equations is actually somewhat complex. That derivation is well documented in other sources. I won't go through the full thing here, but I'm just presenting the final results, the final solution of those equations. So the final solutions of those equations are these two equations right here. So theta 4 and theta 3. Theta 4, 1, 2. So we'll go into what that means. But theta 4, let's just say, is equal to 2 arctangent or inverse tangent of the quantity negative b plus or minus square root of b squared minus 4ac, all divided by 2a. And theta 3 is equal to 2 arctangent of the quantity negative e plus or minus square root of e squared minus 4df all over 2d, right? And these terms, capital B, capital A, capital C, capital E, capital D, capital F, they all are encapsulations of more complex expressions. As you can see here, A is equal to this term, B is equal to this term, C is equal to this term, K1, K2, K3, and then D is equal to this, E is equal to this, F is equal to this, K1, K4, K5. So now the question is going to be, okay, so I have a theta 4 equation and I have a theta 3 equation. What are these subscripts? And you can kind of see, because it's in the form of a quadratic solution, you have a plus or minus, right? So the plus solution represents one answer and the minus solution represents another answer in both of these terms. So the plus solution represents, 1, and the minus solution represents 2, right? So there are two solutions associated with this expression right here, and the same with this expression right here. And you might be asking, why are there two solutions associated with a given theta 2? So what each of these equations is essentially saying is, for a given input angle and a given known set of link lengths, there are two solutions to where the 4-bar linkage could be, right? So if I have a theta 2 that's at 60 degrees and I know my link lengths, these equations are saying your theta 3 and theta 4 have two possible positions they could be in. How is that possible? We're going to go over that right now. So now we're going to understand the different circuits of a 4-bar linkage, open versus crossed, right? So for each theta 2, there are two equally valid solutions to both theta 3 and theta 4. Theta 3, 1, theta 3, 2, theta 4, 1, and theta 4, 2. This is because for each theta 2, there are two configurations or circuits, quote unquote, of the 4-bar, open and crossed. Now, let's look at this diagram to kind of understand what that means. So you can kind of see in this diagram that we have the original configuration of the linkage that we had originally drawn in our geometric diagram, which is, again, this right here, kind of this polygon. This is called the open configuration, and it's called open because none of the links cross across the ground link, right? So this is kind of our open configuration. Now, if you take pin A and you detach pin A such that this link is now free and this link is now free, and you let this link fall across the ground link like this, and you let this link fall across the ground link like this, and then you reattach pin A, This is another circuit or another form of the 4-bar linkage, and it's called the cross configuration because it's now crossing the ground link. The motion profile of the open configuration and the motion profile of the cross configuration are completely different. So when you spin this input link in the open configuration, or you spin this input link in the cross configuration, the motion profiles of 3 and 4 are completely different. And we'll see that in the next video where we do an example problem where we show both the open and cross configurations of a given 4-bar linkage, and we'll see in CAD how they spin very differently. They spin in a very similar way, but kind of inverted and reflected, right? So you can see in this diagram, theta 2 is the same regardless of open or crossed, but we have theta 3,1 for the open, and theta 3,2 goes all the way around for the crossed. Theta 4,1 is in the open, and theta 4,2 goes all the way around for the crossed. So you can kind of see for theta 4,1, theta 4,2, theta 3,1, theta 3,2, we're using the same vector sign convention, we're using the same polar convention, all that stuff. It's just that there are two different circuits of the linkage. And how do you switch from one circuit to the other? Well, you actually have to disassemble the linkage and reassemble it in the other configuration. Again, like I said, you have to disassemble pin A and then bring it from open to crossed, and then the same thing. Once it's in crossed, disassemble pin A and bring the links right back up, and then that gives you the open configuration again. So which configuration your linkage is in depends on how it's assembled, and that's the only way you could change between circuits is assembling it differently. Right? So it's not going to go spontaneously from open to crossed or from crossed to open. If you assemble it in the open configuration, it will be in the open configuration until you change it. If you assemble it in the cross configuration, it will be in the cross configuration until you change it, right? So let's review some of these notes. The configuration is entirely dependent on the way the linkage was assembled. To switch configurations, you disassemble pin A, move links 3 and 4 to the only other positions in which they will rejoin at that value of theta 2. The minus solution should grant the open configuration. The positive should grant the cross configuration. Okay, so in the next video, what we're going to do is go over an example problem where we have a example linkage just like this, and we show both the open and cross configurations. We'll show how they move in CAD, and then we'll use the position equations that we derived right here to show that we get the same answers using these position equations as we get in CAD. And then we can kind of start to develop an intuition for how we can use CAD, specifically SolidWorks, to figure out how we can use those tools to design linkages. Okay? So I really appreciate you watching. Thank you very much, and I will see you in the next video.